In the last video, we were looking at Krishke's section on a more realistic model. And we went over the flow chart. And in this video, what I want to do is the code and the results for a more realistic model. And there were no data in Krishke's example, so I just made some up. And here are the data here. That I'm going to assume that we've got these three coins, A, B, and C. And we've got a series of heads and tails, where a head is coded as a 1 and a tail is coded as a 0. And there is our flow chart. So this data exists in an Excel spreadsheet. So you bring it in, make a data frame of it, and then there's this bit of code here that takes this variable coin and initially is probably coded as a character and converts it into a factor. So although coin may have labels of A, B, and C, it's going to be, those things are going to be stored as 1, 2, and 3 for coins A, B, and C respectively. And so if we look at the data frame, so we do structured data frame, here's what we get. And there's our series of 1s and 0s for tails and heads. And there we've got our factors. And they've got these three levels, which are coins A, B, and C. And so for coin A, that's always going to be a 1. And obviously a 2 and a 3 for coins 2 and 3. So now let's look at Bayes' theorem. And in a very general sense, we can think of Bayes' theorem saying, okay, our posterior is going to be proportional to, and we're able to use the proportional to because what we've done is we've taken the marginal probability of the data, we've held that as a constant, so we ignore it and replace the equal sign in the original Bayes' theorem with this proportionality and say that the posterior is proportional to the likelihood times the prior. And this is a very general form saying, okay, we got a bunch of parameters here, bunch of parameters here, bunch of parameters here. And in this line, essentially what I've done is I replaced this general form with our particular parameters. So we've got omega, kappa, we've got theta, which is indexed by coin, because of course we've got theta 1 for coin A, theta 2 for coin B, and theta 3 for coin C, which comes back to this idea of why we did this thing, because now these coins are actually being stored in the computer as numbers 1, 2, and 3. And so what I've taken is this general form and replaced it by what we've got in our scenario. So I've done that here, here, and here, and here. And the next line is probably the really important line, because what happens in the next line is that we start off with here, and then we factor it out. So you can think that in general, if you had the probability of A, B, and C, that would be equal to the probability of A given the joint probability of B and C times the probability, joint probability of B and C. So that's all we've done here. We just factored that out. But what makes hierarchical Bayesian models so powerful is that this is a generalized thing, but what we've got in this line right here actually makes sense because partitioning it out in this way captures the dependency. Because coin is in the parameter theta for each one of the three individual coins is going to be dependent on the values of omega and kappa. And then finally what we do is we do that. And the reason we're allowed to do that is that these two guys are independent. We're going to assume independence, which to me is a reasonably good assumption. So now we're going to have our model statement. And there's different components to the model statement. We're going to have at the very top, quotation mark, term model, open curly brace, close curly brace, quotation. So we've got matching here. Then what we've got is this bit right here. It's got an open brace there and a curly brace here. And what is this guy? This is likelihood function that says that the values of y are going to come from a Bernoulli distribution with parameter theta that's going to vary among the different coins. And one of the nice things about these flowcharts is that they should line up with the model statement. So here's our model statement, and we can go back up to our flowchart, and that line that I just went over is this relationship right here that says that the values of y arise from a Bernoulli distribution with some value theta that's going to vary, potentially vary depending upon the coin. And so what we're going to do is we're going to have to cycle through this. So we're going to cycle from 1 to n toss. So we're going to have to do this over 30 different values because we had 30 tosses. And we could have put in the value 30 right here as n toss. What we're actually going to do is write in the word n toss, and later on we're going to define that as being equal to 30. The really challenging part, for me at least when I start to think about this, is this line here with this double square bracket nested indexing. How do we think about this? Well, one way to think about this is to think about our data frame and recognize that implicitly these values are indexed by row number. But because we've made coin a factor, we've got 1, 1, 1, 2, 2, 3, 3. So if we ask ourselves, if we look at this and say, what would the value be of theta coin 2? What would that be equal to? Well, there's the row number, I is equal to 2, right here. So what's the value of theta coin? The value of coin when I is equal to 2 is equal to 1. I is equal to 2. The index for coin is equal to 1. So what would theta coin 28 be? Well, if we had theta coin 28, let's do 29. That's going to work a lot better. It'll be a little more obvious. 29. When the row is 29, what's the value of coin? The value of coin is 3, so that's going to be equal to 3. So that's this double square bracket indexing, which, I don't know, I had to struggle a whole lot of time to get my head around that, but, you know, eventually it filtered through. And next what we've got is another loop, open parenthesis, close parenthesis. And what is this guy? This guy is our prior. That says the prior for coin is this beta distribution. And if we come up here, that line of code is this relationship right here. So this was our prior, and there's a relationship. We're going to do this by a loop. I could have put in the value of 3. I'm going to define it as n coin and later on indicate that n coin is equal to 3. It's going to go through that loop. Now, I didn't have to use this loop. As an alternative, I could have said that theta 1 is equal to all this stuff here. I could have said that theta 2 was equal to all this stuff here, and done the same thing for theta 3, but that would have required a lot more writing, but a lot less elegant than this indexing and looping that we've got here. And finally, what we have in these last three lines are our hyperpriors. Those are our hyperpriors, and we've got three different equations, two distributions, and an equal sign. And if we come back here to our flow chart, there they are. There's the two distributions and the equal signs, where we define the hyperprior for omega is this. The hyperprior for kappa minus 2 is d gamma. And then there's an equal sign involved to go from kappa minus 2, add to it to get the value of kappa. And so that's all reflected down here in these last statements. So recall we had this data frame df, and remember what I said was we're going to have to define nTOS and nCoin. So we do that here. We define nTOS and nCoin. We look at the new data frame, and there it is there with nTOS and nCoin. I might note parenthetically that I think I misspoke in an earlier video where I said that there were maybe 28 or 29 flips. There's actually 30, and for coins A, B, and C, the results were 5 out of 10, 6 out of 10, and 5 out of 10 respectively. Okay, so there's our initialization. So if we think about what we've got to initialize the hyperpriors and the priors. So if we come back here to our flow chart, what are we going to need to initialize? We're going to need to initialize is our prior for theta, and we're going to need to initialize our priors for the hyperpriors here and here. And so we see this initialization for theta. We've got three thetas, so we express it like this, and there's our hyperpriors. This is the model statement, pretty straightforward. And finally, we come down here for the results. They're not really that terribly important in this example because really we're just trying to look at the code. So here are the values for omega, kappa, and theta 1. This is kind of what's going on here. Again, I think the problem is we've got so little data that it doesn't really mean much. Same thing here with kappa. You've got obvious problems here. For theta 1, you've got this relationship that looks like that. The final data, if you use the print function, appears like this. You can see that for omega, you've got this huge credible interval. You see for theta 1, theta 2, and theta 3, because our priors were so vague, the posteriors are really going to track very closely on the data, which were 5 out of 10, 6 out of 10, and 5 out of 10 for coins A, B, and C, respectively. So that's the code and the results for a more realistic model. In the next video, we're going to examine an even more realistic model involving therapists.